students, welcome back again. In this part, we will discuss about energy of a simple harmonic motion along with graphical analysis of velocity time, acceleration time and their physical significances. So let's begin. Let's begin with the topic energy in SHM. So in this part, energy in SHM, we would like to discuss if we consider an oscillatory system having SHM, hence the potential energy for a system. So we must know the potential energy. What potential energy is? Potential energy is the energy associated with the position of any system. In the case of a spring, it is elastic potential energy. In case of gravitation, it is gravitational potential energy. In case of any mechanical system, it is mechanical potential energy system. So as in the case of simple harmonic motion, there is a spring block system of mass m and a spring constant k. It executes to and from motion about the mean position. Restoring force is the responsible force that brings systems towards the mean position. In this way, redistribution of energy takes place. Either total kinetic or total mechanical energy is constant, that is sum of kinetic plus potential. So kinetic converted to potential and vice versa take place. So here we would like to discuss the case of potential energy. So according to Hooke's law, we know that force is equal to minus of kx, and we want to know work done by the external agency against that system. So that is equal to minus of force into displacement. So force is equal to minus of kx into dx, and integrating this equation we are getting minus of kx square. So work done by the external agency is equal to minus, or work done by the spring force is equal to minus 1 by 2 kx square. It is just the work done, and potential energy stored in the spring is actually the negative of that work done, that is equal to 1 by 2 kx square. X square if it is along x direction and y direction if it is along vertical direction. So we can discuss. So means we calculated potential energy U is equal to 1 by 2 ky square if the motion is along vertical direction, where the value of spring constant k can be considered as m into omega square, where m is a mass, omega is the angular frequency of that system. That's why we get a common relationship U is equal to 1 by 2 m square. Okay. So I would like to tell you that potential energy is actually the negative of the work done, and that negative is actually integration of f into dx of this term. So we know that it is actually minus of kx into dx, and already when we will solve this equation we will get that is equal to 1 by 2 k of x square. And that's why we got final potential energy U equal to 1 by 2 m into omega square into x square. So means at any time, if we execute, means at any time t, the amplitude is maximum. So what? When the body is at extreme position, its displacement is maximum and its potential energy will be maximum. At that time, it is in the static situation. So kinetic energy will be 0. So if we want to draft it at any time t, so what? Potential energy in terms of time t can be represented by U is equal to 1 by 2 m omega square x square, where x is the displacement at any time t. That can be represented by x is equal to a sin omega t plus phi. On substituting this value in the main equation, so we got U equal to 1 by 2 m omega square a square sin square omega t plus phi. And we draft a graph for this. So we know that U and X, so means we know that U is directly proportional to X square. It is just a parabolic relationship. That's why we draft a graph of this. Now we will switch to next slide. In the next slide we will discuss about kinetic energy. Kinetic energy is the energy associated with motion of any object, as the spring connected with the blow is in motion for a time except extreme and mean position. So what happens? In this part we are knowing that the kinetic energy of the system in SHM can be represented by k equal to 1 by 2 mv square, where velocity v is equal to omega under root of a square minus x square, and kinetic energy k equal to 1 by 2 m omega square a square minus x square. The kinetic energy in terms of time t is given by k equal to 1 by 2 mv square and v equal to a omega cos omega t plus phi. Already we discussed when we have displacement x is equal to a of sine omega t plus phi. So on differentiating this relation with respect to time t, we are getting instantaneous velocity, and we are talking about kinetic energy at any moment or at an instant. So that is equal to 1 by 2 m omega square a square cos square omega t plus phi. And phi is the phase difference from the mean position, and m is the mass, omega is angular frequency. Now switching to next slide, we want to know total energy of the mechanical system. So what total energy in the system is just sum of kinetic plus potential. So means we can say E equal to K plus U, because at it execute SHM motion to and fro. So at these extreme position, it would be in static situations. So at that point kinetic energy will be minimum, but potential energy will be maximum. But at the mean position, we are getting kinetic energy will be maximum, but the potential energy will be minimum. And the sum of this is kinetic plus potential as mechanical energy will remain constant. Only the redistribution of energy take place. So from the principle of conservation of energy, we know that total energy of the system remain constant, that can never be created nor destroyed, but it conserves from one form to another, static to kinetic, kinetic to static. So we know that if we want to find out mathematical equation for this, the equation of the total energy in SHM is given by 1 by 2 m a square minus s square, because we know that V is equal to omega under root of a square minus x square. As we calculated this value, on substituting it in the main equation, we are getting A is equal to 1 by 2 m omega square into a square. Now finally we get E is equal to 1 by 2 k square, because already we calculated k equal to m into omega square, SHM constant. So we know that kinetic energy means E is directly proportional to k is constant. A is also a constant because it is a condition for maximum displacement, that remain constant always. So we would like to draft the graph of the different terms, like we can see. First of all, we would like to draft the graph for displacement. In this graph we are getting, so already we discussed displacement can be represented by x is equal to a sine omega t plus phi. At any time t, the displacement x is equal to a sine omega t, phi is the difference. Phi can be either 0, it can be either negative, it can be either positive. If it is leading, it would be positive. If it is lagging, it would be negative. If it is in the mean position or it is in the phase, it would be 0. We can draft 3 conditions for this. Means if it is at mean position, we can say it is this one. At time means phi is equal to 0. For the second part, if it is leading, so means we can say dotted part. So means when phi is positive. So we can say the value if it is positive A. So we can say phi for this is equal to sine inverse A. But if it is lagging, so what we have to do? We have to consider this part. So means it started from this negative part. Phi is equal to sine inverse A negative. And we know that sine is just an even function. So phi will be minus of sine inverse A constant value. That's why it is a case of lagging. So we have 3 different cases: leading, lagging and mean position. That's why it is for the in phase equations, where maximum displacement is given by A and time for one complete revolution is 0 to t, and it becomes maximum at 2 points. I would like to tell you that particles are the main cause. Particles are the main cause that executes, because these particles are executing their motion about mean position, and they constitute a wave that transport energy as well as momentum. So we got phi equal to a sine omega t, that is just a sinusoidal function. Now in the second part, we would like to say that in the second part, if we have an equation x is equal to a sine omega t plus minus phi, that can be equal to a this one. Means if it is given that phi is equal to positive or negative. If it is given as positive, we will say x is equal to minus 0. So mean it is started from the negative of displacement, like that. In the reverse phase, we can see. In the second part, we are knowing that General equation of a velocity as a function of time t in SHM if phi is equal to 0 can be represented by v is equal to a cos omega t plus phi. We got this value on differentiating the displacement equation. So if we put phi is equal to 0, we got velocity v equal to a omega cos omega t, and we know that we are in condition to draft the graph of cos with respect to time t. So the graph of cos function with respect to time t will start its value from a, and that is just the maximum amplitude. So a omega can be taken as, we can say it is positive r. So we can say v equal to r into cos of omega t, and negative r is the value of this function, and we draft the equation of the graph like this. So these are the graph of SHM. Second part, from the relationship between velocity and displacement, we got v equal to omega under root of a square minus x square. Already we discussed part in the previous slide, but once more I would like to explain you why it is given an elliptical form. Actually, we know that we already calculated this equation y equal to omega a square minus a square from the displacement. On differentiating displacement, we got v equal to a omega cos omega t plus y. Changing cos omega t in terms of a and x, we are getting v equal to omega a square minus x square. And actually, it is just the graph of ellipse, in which it is just the semi-major axis and it is just the semi-minor axis. So we need to know on squaring both sides, we got v square equal to omega square a square minus x square, or we can say v square equal to omega square a square minus omega square x square. So we got v square plus omega square x square equal to omega square a square, or we can say v square upon omega square a square plus x square upon a square, that is equal to 1. On comparing this with the main equation, x square upon a square plus y square upon v square, that is equal to 1. So a and b are the intercept along x-axis, and y means along major axis, semi-major and semi-minor. So we are getting a and b. So it is just for x, it is just for y, and that's why we got an elliptical equation for this relationship. Now we would like to draft the graph for acceleration and time t. So we already discussed this part. If we have mathematical equation y equal to a sin omega t, on differentiating it with respect to time t, we got velocity. For the acceleration, we will again differentiate it, and we are getting a equal to minus of a omega square sin of omega t plus phi. Now at time t equal to 0, phi will be 0, means at initial phase a equal to minus a square. So mean it will start its motion from the mean position but in opposite phase. So we will draft that, as we know that x is equal to a sine of omega t. So its graph was actually positive x direction, but when we want to draw the graph for acceleration, easily we can see in the main equation over here. So means at time t equal to 0, acceleration will be 0. At time t by 4, its acceleration will be maximum. At time t equal to t by 2, it would be again 0. At t equal to 3t by 4, its acceleration will be maximum, and at t it again 0. So we are getting at mean position or equilibrium. At equilibrium position, acceleration is always constant, means 0. Now we would like to switch to the next graph, that is in between acceleration and the displacement. So we can see here in the graph, if we have the equation a equal to minus of omega square into x, means x is the displacement at any time t. We want to draft the graph between acceleration and displacement. Easily we can say it is just means y equal to minus of m into x. Y, that is a equal to minus of omega square into x. So we can say the graph can be seen directly over here, that passes from the center. Now we would like to know what is gradient in this part. So gradient is actually the slope. It is actually the slope. So means either it is dy upon dx, or we can say that is del acceleration upon del x. So we can say dA upon dx, and that is equal to minus of omega square. Actually we got it as gradient. Gradient means any physical quantity that changes with respect to the radius, that respect to position from the center, from the mean. Means for any physical task there is a reference point. If that physical quantity like energy, maybe potential, maybe acceleration, maybe velocity, maybe displacement, like that, if it will change with respect to position, so the change of that quantity with respect to radial distance or displacement is called as gradient. And actually it is just a slope also if the graph is given. Now we would like to switch to the graph question over here. In this question, we are given the displacement of an oscillating body object as a function of time t is given by, it is just a sinusoidal graph. You can say 15 is the maximum amplitude minus 15 is the minimum, that is in centimeter t. So time, one complete revolution is 0.8 second. In the first part, it is about the amplitude. So we can say amplitude means writing this equation that x is equal to a sine of 2 pi by capital T into t, or we can say x is equal to 15 into sine 15 upon 100 centimeter into sine 2 pi upon 8 into t. So on comparing the equation, we are getting amplitude is equal to 15 by 100, that is equal to 0.15 meter. The period is given as t equal to 8 second, and frequency is always 1 by capital T, that is equal to 1 by 8, and it is equal to, we can say that 1 by 8 hertz, we can say, leave it. Angular frequency is actually omega equal to 2 pi into t, or we can say 2 pi into frequency, so we can say 2 into pi into 1 by 8, that is pi by 4 per second. So now radian per second, we can say it like that. So they are talking about frequency, it would be per radian per second. Now part C, the equation of the displacement as a function of time t. So already we calculated that x is equal to a of sine 2 pi into frequency into time t, that is, we can say that is x is equal to 0.15 sine of pi by 4 into time t. So it is equation of displacement. Equation of velocity, we would like to differentiate. So v equal to dx upon dt, on differentiating we are getting 0.15 multiplied by pi by 4 into cos of pi by 4 into time t. So it is the equation of the velocity. And acceleration, we will again differentiate the relation, and we know that it is just equal to minus omega square into x. So omega is already we calculate pi by 4, so that is minus pi square by 16 into x is given as 0 multiplied by 0.15 into sine of pi by 4 into time t. So simply we will get the equation of acceleration on differentiating displacement, or equal to minus of omega square into x from this. Now in the last part we already did this part. So in this question we are already given the equation of displacement, x is equal to a sine omega t. So on comparing it with the main equation, we will get amplitude, period and frequency. For the next part, that is angular frequency. Angular frequency is 2 into pi into f. F is the linear frequency. And now the equation of the displacement is a function of time t. So we will like to displacement mean from the given data we will draft the equation and we can easily find. It should be the first part in the question. Now option D means the D part, the equation of the velocity and acceleration as a function of time t. So we know that velocity is just the rate of change of displacement. We will differentiate the main equation we got and we will put the values in the equation, and acceleration is just the double differentiation of displacement. So easily we can find the answer of these 4 questions from the given data as we have. In this part, we discussed about energy involved in a simple harmonic motion along with the graphical analysis of velocity time, acceleration time. I hope you understood the topic. Now, in the next part, we will discuss about again SHM analysis of acceleration time, energy graph, that is the functions of displacement, and also the phase difference relationship, whether lagging, leading or mean time. So stay tuned with us.